suppose we have cumulative density function, which would look like this. Cumulative density function would be cumulative density function would be look like this. So this is 1/2 and look like this. So our strategy is to generate uniform distribution, random number from uniform distribution in this area, and find inverse image of a random number, and then generate this one. So this is a random number 1 from standard normal distribution, and we pick another number around here maybe, and this price. This is random number 2, something like that. In this process, we can throw lots of number around this center and less small amount of number from this region, because to select number in this region, we have to generate uniform distribution from this small area. So it is normal distribution. Norms means normal distribution, and S means standard normal distribution, and then inverse, and then generate uniform distribution, and it is one random number, and then now we have this is a 10 random number from standard normal distribution. So if we click F9, yes, it is refreshed. And then to generate stock price. Stock price is basically looks like this. So let's say current stock price as 0. So stock price at time t is, I'll explain to you the formula first. Let's say S0 is stock price today, and stock price t times later look like exponential, okay, and then mu minus 1, okay, sigma square divided by 2 multiplied by t plus, okay, s, and then z. Let's say z is the random number, and then t. So yeah. Here mu is expected return, and S is the standard deviation or volatility. So everything is per year, so annualized. So everything per year, and the T is time. So it is a year. Okay. So when T is 0.5, it is like a 6. Okay. It is like a 6 months. When T is 2.5, it means 2 years and half year. And then Z is a random number from standard normal distribution. Okay, so it looks like this. So to write it to you, it looks like S. So ST equal S0, today's stock price, and then E, and mu minus sigma square divided by 2, and then time to maturity plus sigma, and then epsilon, standard normal distributed, and root t. Okay, sorry, I forgot root here. T 0.5. Okay, so let's think about the intuition. Okay, intuition of this one. So if we take log of each side, okay, take log of each side. if we take log of each side, then and then move, if we take log of, so if we divide each side with S0 and take log, and then we have something like this. Nu minus 2/2 sigma square T plus sigma epsilon root T, right? Something like this. But then think about this one, this term, right? What does that mean? It is the holding return. So if you hold on, if you buy stock at time t, so it is like holding period. It is called holding period return. It means actually it means how much you actually make money. So if you buy stock at time 0 and hold the stock up to time st, and then this is basically how much you will make. It is like a return. Of course, since we take log, it is continuous. Okay, it is not discrete time. It is continuous. Okay, continuous holding period return. And then of course the volatility is, yeah, let's say, so it is we don't know what will be the stock return for the next t years, right? There is always uncertainty, and then uncertainty is captured by this part. This part, epsilon is drawn from, right? Epsilon is drawn from normal distribution, normal distribution, 0 to 1, okay? So, normal distribution, so on. So as time, okay, if t is large, it means a future, more and more future. The bigger the t is, the more the future, right? The further the future. So for the future, there would be more uncertainty. So if we take variance, calculate variance of this one, so think about computer variance of continuous holding period return. This term is basically constant, so this term drops away. So variance is entirely determined by this one. So variance of this one is simply sigma square t, right? So variance is basically, think about this. Variance is simply, right, sigma square t. And that this one makes sense, right? And sigma is like a per year volatility, per year variance. And then if stock return is independent each time, today's stock return is independent of tomorrow's return, then when two random variables is independent, the sum of the variance is variance of a sum of random variable is actually sum of the variance, right? Variance x plus y is variance x plus variance y when x and y are independent. So basically stock is independent, we can just add variance. So when time is t, we are just adding variance for time t, right? So it actually makes sense, right? So if we set this stochastic term sigma epsilon root t like this way, then we can make variance sigma t, which has a nice property that variance increase over time, and it's proportionally as if stock return is independent of each other. And that actually makes sense. Stock return should be, if market is efficient such that no one can make money by simply observing today's stock return, then stock return should be independent, right? Today's stock return should not contain any information about future return. It means they should be independent. Independent, then variance should be proportional to the time. So this term makes sense, okay? So this is okay. So this term seems a good idea. This second part, so therefore, this second part, good idea, okay? Okay, second part captures variance term. Then what the first part can capture? Let's think about the first part. The first part is simply we take expectation of each side, then expected return. expected return. Let's think about expected return. Then expected return is mu minus 2 over sigma square. Okay, like t. Okay, so mu is expected return. So it means that, of course, per year, if we generate expected return like mu, for the next t years, it should generate expected return like mu multiplied by t, right? That would be our guess. But then the question is why we have minus 2 sigma square over 2. Okay, that seems a bit strange, right? Okay, so basically we want to capture expected return using the first part. 김민정 쌤, 오늘 발표가 있으면 빨리 오든지 나한테 연락을 해줘야 될 거 아니야. 몇 시에 연락했어? 응? 내가 9시에 수업 들어오면 한 8시 50분쯤, 55분쯤 되면 핸드폰을 끄겠지. 근데 그때 전화해서 내가 뭐 수업하고 있는데 받았어, 전화를. 내가 지난 시간에 웃으면서 좋게 이야기했더니 전혀 먹히지가 않아. 너무 불성실한 거 아니야? 하기 싫으면 어차피 이 수업은 뭐 여러분의 자발적인 참여에 의해서 이루어지는 거기 때문에 하기 싫으면 안 해도 돼. 네? 그냥 발표하기 싫으면 안 해도 되는데 하겠다고 해놓고 차질을 주면 안 되는 거지. 나도 그냥 늦을 것 같다, 못할 것 같다고 미리 이야기하고 그냥 안 하면 돼. 알았어요? 잘 합시다. 네. 사회 나가면 그러진 않을 거 아니야. 김밀량 학생이 취직하는데 네? 솔직히 학교 수업이 만만하니까 이러는 거지. 직장에서는 이렇게 행동 안 할 거 아니야. 월급 주고 이런 직장에서도 이럴 거예요. 아침 9시에 과장님이 김밀령 씨 와서 발표 좀 하라고 준비해 온 거. 그랬는데 한 20분 늦게 나타나서 연락도 안 해. 연락했다고 하는데 회의 직전에 연락해. 회의하려고 핸드폰 꺼놓고 있는데 회사라면 그러겠어요? 절대 그렇게 못하겠지. 왜냐면 회사에서 월급 주고 그 다음에 그렇게 행동하면 회사에서 자를 테니까. 근데 학교는 만만하니까 지금 이러고 있는 거 아니에요? 솔직히. 항상 앉으세요. 네. 아무튼 제가 뭐 여러분이 공부하기 싫으면 안 해도 되고 솔직히 내가 뭐 여러분의 부모님도 아니고 내가 뭐 어떻게 할 수 있는 방법이 없어요. 근데 최소한 다른 사람한테 피해만 안 주면 돼요. 공부하든 안 하든 학점을 어떻게 받고 취직을 하든 말 그건 다 자기가 책임인 거고 단지 다른 사람한테 피해만 안 준다. 그리고 이건 모든 게 자발적인 참여에 이루어지기 때문에 내가 여러분한테 하라고 한다고 해서 하기 싫으면 그냥 별로 발표하고 싶지 않습니다 하면 괜찮아요. 안 시킬 거야. So anyway, about the first part, expected return. So about expected return is about, it has 3 parts, actually 2 parts. Part in the, yes? Oh yes, mu is expected return. Oh, so expected return of holding during holding period. By holding, okay, let's be specific. By holding, okay, holding the stock. So mu is like return per period. Okay, what do we expect return? And then this one, this whole thing is how much we will make in expectation. Okay. By holding the stock for the next t period. Okay, so by multiplying t max, if expected return is 1%, if we hold 1 year, 10 year, 1% per year, and 10 year it should be 10%, something like this. So multiplying t makes sense. Multiplying t over mu makes sense. Then the question is why we subtract sigma square root t. Okay, this is a bit harder to explain. It is called convexity adjustment mathematically, and if we use mathematics, it is easy to prove. Okay, easy to prove. But in this class, instead of using mathematics, let's think about it. Think about it with examples and with intuition. So let's think about this case. So let's say mu is like 1%. Mu is like 3%, okay? 3%. Mu is 3%, and let's generate stock return 1, 2, 3, 4, 5. Next 5 years stock return. So stock return is basically then let's say F4 plus okay, let's make it even simpler example. Okay. So 3%. So this is 3%. 3%, and then this is let's say minus 10%, minus 5%, 5%, 10%. Okay, suppose my stock return per year looks like this. Then the expected return is 3%, right? Right? It is 3% because 3% is add them all, right? And divided by 3, then it is 3%, right? Right? It is 3%? No, I don't think so. Sorry. Yeah, it is actually, yeah, no. How can I make it expected return 3%? Minus 5%. This one minus 10%. And this one plus 5%. And this one plus 10%. Okay, then it is the average is, of course, average return is 3%, right? It should be 3%. So it is stock 1. And then let's think about it, stock 2. Stock 2 is, let's say, it is very simple, 3%. So it is average is also 3%. Right? So both of them is 3%. Okay? Both of them have the same mu in our previous example, same mu. But then let's think about our holding period return. Okay, holding period. Suppose we invest $100. Okay? So invest stock price, let's say S0 is $100. S0 is $100. And if we invest $100, then the first year is $100 multiplied with 1 plus this one, right? And the second year, okay, it should be this one multiplied by 1 plus this one, right? That should be the value of our asset. And if we keep doing that, okay, then my final return would be look like this. My value of my final asset is what? It looks like this, 14%. And then if we divide this one by 100, it is the, and then minus 1, it is like a 14% over 5 years. So it means that in this scenario, we basically learned like 14, like almost 15%, 14.6% per year, right? It makes sense, right? Stock price sometimes go down and go up, but basically since average annual return is around 3%, I made money. And then if we make it annualize, and then 1/5, and it means, oops, sorry. If we annualize it, interestingly, it is actually less than 3%. Okay, let's think about this case. So in this case, stock return is always 3%. So first year is 103, right? And the second year is 103 multiplied 1 plus 3%. So stock return would be something like this. And then it is exactly 3%, right? It should be exactly 3%. Actually, it should be, right? In some sense, it should be. So both of them have same expected return, same return per year over the 5 years, same expected per year. But thing is that first stock has a volatility, and the second return does not have volatility. And since it has volatility, actually its holding period return is lower than 3%. Right? Right? Do you know what I'm saying? So again, both of them is the same 3% per year. Okay. So actually, when you suppose you are to invest your money in a mutual fund, and they may advertise, the fund manager or the asset management firm may advertise that, okay, our assets generate like 3% per year, something like that. But it does not mean that actually you will make 3% per year if you hold the stock for multiple years. Okay? Although fund manager says that we make money like 5% per year, it does not mean that you actually make money 5% per year by holding the stock more than 1 year, multiple years. No. You also have to check the volatility of their performance. So if the volatility is high, that is definitely should be lower than 5%. As if the volatility is greater than 0. If there is a risk in the stock return, your holding period return per year is always less than that 5%. Okay? So we have volatility and we have to adjust down your actual holding period return. Okay? And how much we have to adjust it down? Okay? This is equal to this amount. We have to subtract. Okay? We have to think about everything in continuous time. Okay? Continuous time return, continuous holding period return. We have to subtract sigma square over 2 by this amount. So it makes sense now, right? If volatility is high, then we are adjusting down holding period return more and more, right? If volatility is 0, okay, if stock return does not have any risk, then the sigma square is 0. So your return per year becomes actually holding period return. But as far as volatility, this sigma is greater than 0. You have to always adjust it down. Okay? That's why we have this term. Although per year expected return is new, actually we have to subtract this down in order to make it holding period return. Okay? That's why our stock return process should be look like this first line. Looks like this one. Do you have a question? Does it make sense? Yes. Yes, exactly. So it is an expected function. So thing is that, okay, let's explain very intuitively. Okay, very intuitively. So expected, think about it, what would be look like expect function of exponential function. Okay, exponential function look like increase this one. Okay. Okay, so if you think about exponential function would be look like this. Okay. So exponential function, it is the exponential of x. So suppose you generate return, this is, let's say, R1, return of the first period, and this is the return of the second period, something like that. And then if your fund manager says that, okay, our return per year is something like that, then he means that average of those two, right? This is expected return of the average, right? Right? Average, right? Then it means that, okay, expectation of the average, something like that. And then it means that, okay, let's connect this line together, and then so basically what you are gonna make this one, okay, so it means that no, this is not a correct way of explaining this. So basically what we want to compute is that, okay, this part is, this part is expectation of, okay, this point, the height of this one, okay, this is the expectation of E exponential x, okay, and then this part is exponential of E multiplied by x thing, right? And then from this relationship, since it is convex, we know that E exponential of x is greater than, always greater than E expected return of the x, something like this. And then I'm arguing that, okay, like this. So in this case, so think about this one. So this one is, while I'm calculating this one, if we think it in terms of exponential function, so exponential, then let's say this one multiplied by expected return of this one. Expected return of this one, and then like this. No, this one is then this one multiplied by expected return of this sum. If we think everything in continuous way, Okay, and then this one. Okay. This is slightly. This one is a bit. This is. I'm confused. Okay. So let's say ln this one divided by this one 15% and divided by 5, then is exactly 3%. Okay, it should be exactly 3%. Yes, actually it should be. This is yes. Actually, it is a good question. I'm confused. I'm kind of confused. Yes. This is 3% one. So it is like in the first case, I'm simply putting 1 plus R 1. Basically 1 plus R2. Okay, so holding period return is basically this one minus 1. Okay, for 2 years, the holding period for n years. For n years, we have to. What I have to do is R2 1 plus R n. Then in this period, our holding period return is 1 over n minus 1, right? This is our holding period return for n years. And then basically I am interested in computing this. Yes, I am interested in computing this. Okay. This term doesn't matter. So I am interested in expectation of this one. Expectation of this one, and then we are comparing this one versus some versus, and then 1 plus actually expected return. Right? We multiply the same thing, and then we are computing 1 over n. We are expectation of this one. And then anyway, this one doesn't matter. And then when we just saw that this one is greater than this one, so the second part is greater than the first part, right? Oh, yes. Actually, so this is, I'm sorry, this is the different from. So, okay, as you can see, actually I'm a bit confused. This is not correct one. So again, let's think about the two case. 1 plus R1. Let's think about 1 plus R2. Okay, and then actually more correctly, let's think about 1 plus R plus epsilon 1. Okay, so epsilon 1 is random number from standard normal distribution. And then it is a two period return, R plus epsilon 2. And then our holding period return for this two period is this entire thing multiplied by 1 over 2. Right? And then this is actually our holding period, is a holding return. But instead, if we are simply plugging the expected value is 1 plus R square and then 1/2, which is basically simply 1 plus R. Right? And then we just saw that the second term is greater than the first one. Okay? In general, it should be 1 over n. This term is 1 over n. But anyway, this term is less than 1, right? Always less than 1. If it is a multi-period return, it is less than 1. So it is like this term would like a function of x 1 over n. Something like this. Looks like this. X 1 over n. Then it is actually not a convex function. It is a concave function, actually. So x 1 over n would be look like this one, right? Looks like this one, actually. Okay. It is a concave function, right? So root x, think about it. So this is the root x would be look like this, right? So let's say this one is R plus epsilon 1. And then let's say this is R plus epsilon 2. And let's say this is R. Okay, R. So let's say epsilon is minus 0.5. And let's say this one is a plus 0.5. Okay, then in these two cases, expected result is exactly same. Okay, but thing is that is R minus 0.5 is R plus 0.5. So expected return of these two cases. Okay, expected return of these two cases. It is hard to draw straight line in this one. And then it's something like this. This point, it is 2, and then it's 1, and this is 2. Okay, and in case of 1, okay, it is average of this one and this one, so it is the center. So this is 1, right? So this one, same length. And this one, same length. So in this case, convex we have to convex adjustment. Actually, we have to adjust it down. Okay. Adjust it down, right? So actually, what we are actually making money, okay? Because we are making money of the either this point. Actually, sorry. Actually. Yeah. And then this is actually 2. Okay. This is 2. And sorry, this is the. Okay. We have to ignore this one. I'm sorry. Okay, so if we simply plug, okay, this one, if we simply use expected return of this one, then if there is no uncertainty, then per year, actually we are making this amount of money. Okay, but actually what we are making money is either this one and this one. And we are making average of this one. So this is actually what we are actually making. So this is 1 and this is 2. And then as you can see, 1 is always less than 2. Okay. So I mean, I was a little confused, but it is actually concave function. If it is multi-period function, actually it is concave function. Therefore, what we are actually making money is average of this point, which it does not mean that once we take average of these 2 points and then this one, okay? So this is just not possible. But of course, if there is no risk, then if we make this money, then our holding period return is exactly this point, the higher. But if we have more and more volatility, then the distance between this one and this one is farther away. If we have more and more volatility, then we are, in this case, we are taking average of this one and this one, and then our expected return becomes even lower, right? This point. Okay. So as we have more and more variance, we have to adjust down our actual holding period return more and more. Okay. So I was confused. So I mean, our holding period return is actually concave function, not convex function. So we have to adjust it down for convexity adjustment. Okay, good. So is everything okay? Felix, do you understand what I'm saying? Not exactly. So. But you can understand this Excel sheet, right? At least you can understand what is going on here. So yes, actually I'm explaining this one graphically. Okay. So the performance of this one is actually looks like this, convex function. And then I am taking the average of the 2 points, so which is lower than. So since it is a concave function, concave means when you look at the function from the bottom, it looks like dome. It is concave function. So average of my performance, does not mean the performance of the average. Clear difference. Concave function of expected value is always higher than expected value of concave function. That's what I'm saying. Any question? Okay, so when we actually generate stock price, now we can simply use this one. So let's say mu is this one, then what we can do is simply, let's say sigma, let's give sigma like, let's say mu is, so this is G, okay? This is G. And then let's say mu expected return is per year like 7%. Volatility, what was the volatility of world to Disney? It was like 20%, right? And then time to maturity. So I want to simulate stock price of world to Disney like 5 years later. Looks like this. And then stock price of world to Disney is price of Wall Street is this one, 9.22. So S0. Stock price of Wall Street today is this one. Oh, $90. Okay, let's say $90. Then stock price of Wall Street at time t later, and we can simulate this one as the stock price of today multiplied by expectation exponential function of mu, okay, minus this is sigma square divided by 2 multiplied by time to maturity, time, okay, and then plus sigma multiplied by this one random number, and then square root of the time to maturity. Okay, but then yes, and then I have to put absolute value for everywhere. No, except this one, okay? Except this one, 8, which is general random number. Okay, so this is good case, right? Let's see. So I'm generating stock return of the, okay? This is a bit dramatic. Okay, they are very dramatic, but that is fine. So when stock price of World Disney 7% simply too high, let's say 3%. Okay, today's stock price, World Disney stock price is 9%, and expected is 3%. So per year it grows around 3%. But it does not mean that we actually, of course, make 3% per year. Actually, it just grows 3%. So in this case, the shock during the period of the next 5 years, there is a negative shock, right? Negative shock. So actually stock price went down. In this case, we have a positive stock, so stock price go up, right? And it is a very negative shock, so stock price goes very down, right? Like this. So this is the, right? So this is the way of simulating stock price of the Walt Disney like 5 years later. Okay? And we just simulate like 11, 10 random 10 stock price, but of course we can generate more stock price like this. And actually we can also simulate everything in one step because we now know how to simulate standard normal distribution. So one step means this one multiplied by exponential multiplied by another this one mu minus sigma square over 2 multiplied by t plus sigma multiplied by sigma multiplied by, and then root t, and then we have to add shock from standard normal distance, which we know how to do it, which is norms inverse, okay, when, right? Done. So it is one stock price, therefore, right? Oh, yes. Sorry, I have to add a expected value of everywhere, absolute value everywhere. Okay, so I am generating Walt Disney stock price more easily, okay, like this way, a lot of time. Okay, so this is the way of generating stock price, and by generating stock price for future stock price, then we can calculate derivative price for each case, and then we can calculate the value, expected value of derivative price of it. That's our work. But before we are doing that, actually my plan was to calculate a concept called value at risk today. Have we ever heard of value at risk? Have we ever? Yeah, so this is a very important concept, especially in practice. I don't think it is that important in academia. It is such a simple concept, but in practice,